Yes, so welcome everybody to our quasi-world seminar. As you have seen from the email that Misha sent around, so we will have the seminar, I think, once a month, every Wednesday, 8 a.m. LA time, always the first Wednesday of the month. So let's get to our first talk. So the speaker is Zach Smith, and he will talk about the Thurston pullback map. So please, Zach.
All right. Well, hello, everyone. I guess it's an honor to be the inaugural speaker for the Quasi-World Seminar. For those of you who don't know me, I'm a graduate student at UCLA. Mario Bonk is my advisor. But yes, today I'm going to talk about the Thurston pullback map. I guess probably most people here are a little bit familiar with this topic already. It comes up quite a bit. And also, hopefully I don't have too many things that are incorrect on my slides because most of the people I'm citing are present in the meeting, I believe. Okay, so let me first talk about a motivating example here. So we could consider this rational map, f of z is equal to 1 minus 2 over z squared, as a map from the Riemann sphere to itself. Right, and we can ask, dynamical questions about this map. And, one thing that we can do to, I guess, study the dynamics is to, understand where this map sends critical points. So for example, the critical points of this map are going to be 0 and infinity. And this can be, seen by looking at derivatives, for example. And 0 will map to infinity, and then infinity will map to 1, and then to minus 1, and then it'll actually just get stuck there. Okay, so this gives us a notion of what's called a postcritical set, and then this is going to be the set of all the points that are eventually images of critical points under iteration. Okay, now the main, I guess, property that I'm interested in for the moment is the fact that if I look at this this map F and I delete on this side the postcritical set and on this side the preimage of the postcritical set, F inverse PF, all right, then this is going to be a covering map. Okay, and this particular covering map is going to have, I guess, interesting properties when we look at the preimages of curves, and we'll see that in a second. But this was just a special example here, this rational map. We'd like to, look at a more general class of maps today, and that's going to be branched covering maps, or more specifically, Thurston maps. So for those of you who aren't familiar with these definitions, a branched covering map is going to be a map from the sphere to the sphere. It's going to be continuous and orientation preserving. And in local homeomorphic coordinates, it's going to look like z maps to z to the d. And I guess in one of these coordinate neighborhoods, this integer d is going to be what we call the degree of the function at that point. So a critical point is going to happen whenever this integer d is going to be at least 2. Okay. So that was a branched covering map. What is a Thurston map? Well, a Thurston map is going to be a map that has that property that I talked about at the beginning. Okay, so we iterate the critical points and we obtain this post-critical set. And I guess the key thing here is we want this post-critical set to be finite. So a Thurston map is going to be a branched covering map, and it's going to have finite post-critical set, just like the first example. Okay. So here's another example, I guess, that'll be of interest later on, which is the lattice map. So a lattice map is going to be constructed in the following manner. We're going to have this, what we call the Euclidean square pillow. Basically, what I've done here is I've taken, one copy of the unit square and a second copy, right? And then I identify these boundary edges. So here, and then I guess here and here. Okay, and then I end up with something that looks like a pillow, and this is going to be homeomorphic to a sphere. And then there's a way that you can define a map by subdividing this pillow, I suppose. So the way that this works is, we start off, let's say, in one small corner, right? And we imagine a map F that scales this corner up to the entire thing, right? Let's say, just by dilation. All right, and once we've defined the map on this corner here, we can actually extend the definition of the map from the corner to the entire sphere just by Schwartz reflection. So that's how I get this tile coloring on the left-hand side here. If I change my color. So, let's say I'm interested in this square now. Well, that red square is going to be reflected across, let's say, this green edge. All right, so to get that, I just reflect across this green edge of the pillow, and then that puts me on the back side of the pillow. So I guess we have a red square on the back here. And then I just continue Schwartz reflection until I fill out this entire quilt. And you can do this for any n. This example here is going to be a 4x4 lattice map because I've divided my pillow here into 4 squared tiles. Okay. And the lattice map is, an example of something that's going to have finite postcritical set. And also, if you sit down and you work through it, you'll be able to determine, I guess, a rational map that models the behavior of this map. And this kind of leads to a very important question in the theory of these Thurston maps, which is, when exactly can a Thurston map be realized in some sense by a rational map? Thurston maps, again, were a topological model of rational maps with finite postcritical sets. So, it should be possible to say when exactly that happens. And this realization here is, it's up to some kind of topological conjugacy. So, F will be topologically conjugate to some rational map, but it won't quite be normal conjugacy. Because what we need, I guess, is 2 maps that are isotopic relative to postcritical set. So maybe I should actually just draw a quick commutative diagram here to explain what's going on. Okay. So all the corners of this diagram are going to be the sphere. And we would say that F is going to, be equivalent in some sense to G, in the sense I'm interested in, when H1 is isotopic to H0 relative to postcritical set. Right? And these are homeomorphisms. Okay. So there's a pretty famous criterion due to Thurston that tells you when exactly you can be realized by a rational map. And I'm not going to explain what all the words in this theorem mean, but it happens when there's what's called an invariant multicurve. All right, and it needs to have, well, this is a spectral radius, right? Or equivalently, you can think of it as some kind of eigenvalue. But you need this multiplier here to be less than 1. But we aren't going to, be interested in, I guess, this statement of the theorem too much today. will be more relevant to us is going to be the second statement. And I'll explain what these words mean a little bit more later on. But there's going to be an induced map on Teichmüller space associated to a Thurston map. And it turns out that at least when you have a hyperbolic orbifold and at least 3 postcritical points, you're going to be realized by rational map exactly when this map on Teichmüller space is a fixed point. But that'll come later. Okay, so now I want to talk about I guess what I alluded to at the beginning, which is what exactly happens when I look at preimages of curves of one of these Thurston maps. So to do that, I need to first introduce some terminology here. So I want to talk about, I guess, the classification of curves in a marked sphere. Okay. So a marked sphere is just going to be a sphere that has some finite collection of points V. All right. So in this particular picture, I have 1, 2, 3, 4 points. And then we say that a Jordan curve, a simple closed curve, is going to be essential if it goes around at least 2 points in my marked set. And we're going to say that it's going to be peripheral otherwise. So I have some nice color coordination here. But as you can see, this blue curve goes around 2 points in our marked set. So this is going to be essential. And then this green curve here, well, depending on your point of view, it goes around either 3 points in my marked set or 1 point in my marked set. But in either case, it's going to be peripheral. Okay, and we're going to treat a null homotopic curve in S2 minus V to also be a peripheral curve, right? So something that encloses, depending on your point of view, no points or 4 points. Okay. This is, I guess, going to be useful for us because at least when we're in this essential case, essential curves are going to have some nice properties when I look at preimages. All right, so as I talked about before, for these Thurston maps with finite postcritical set, we're going to get proper covering map when I restrict the domain and codomain appropriately. And if I have an essential curve in my target, then when I take its preimage, if that happens to be the preimage is also going to be a Jordan curve. Yeah. Okay. So the preimage is going to close up. It's going to be a Jordan curve. And if it just so happens that one of these preimage curves, which we call pullbacks, are essential, then the isotopy class of that pullback is only going to depend on the isotopy class of the curve on this side. All right, at least that's going to be true in this case where I have 4 marked points. And this case where I have 4 postcritical points is actually really going to be the only case we talk about today. Okay, so if I take the pullback of a simple closed curve, I guess simple closed curve, and I know that in some sense it's going to be well defined up to isotopy when both are essential. So this allows me to define a function here. Okay, so one thing I haven't mentioned yet, since I'm specializing in the case where I have 4 postcritical points, these essential Jordan curves are actually going to be in bijection with the extended rational numbers. And I'll explain why this is the case a little bit more in a second. But I guess the key thing that I want to focus on right now is that we can define a function that sends the equivalence class that this curve belongs to the equivalence class that one of its pullbacks belong to. All right, and then if you believe me when I say that these equivalence classes are in bijection with the extended rational numbers, then this defines a function on the extended rational numbers to the extended rational numbers. Plus, the peripheral curve, we pretend that the peripheral curve gets sent to itself. Okay. So yes, that's going to be the slope pullback function. All right, it's going to send a rational equivalence class to the rational equivalence class corresponding to the pullback underneath the Thurston map. So let's look at this in a very specific example. So let's look at something that's somewhat similar to our lattice example from earlier. What we have here is a map where we start off, I guess, in the same way. We have like the identity on this Euclidean square pillow. But rather than subdividing this pillow, I cut open some arcs. So I can cut open an arc on the bottom, on the left, and on the right. And I can attach to it, I guess, new squares. And then I can extend, the map from this white tiled base pillow to, these flaps just by source reflection again. So obviously you're not going to be able to see this in the coloring, but there's a backside to all this. It's also going to be T-shaped. The backside of, let's say, this bottom flap is going to be a white tile, meaning that it gets sent to the front half of this pillow here. I guess does the definition of this map make sense? Does anyone have questions? Okay. And we see here I've marked 4 points at the corners, and these are going to be my postcritical points. And I'm in this case that I said I was interested in. I have exactly 4 of them. Okay. So here's an example of the sort of picture that you can get when you look at the slope pullback functions. So I guess the representation of this Jordan curve as a particular slope makes a lot of sense on this side, because this is literally going to be slope 5 halves in this picture here. But this isn't how we, I guess, count I guess like the numerator and denominator of these slope classes that I'm interested in. So the correct way, I guess, to associate one of these curves to a particular slope is to look at intersection numbers. Okay, so what we do is we draw in arcs in our surfaces here that connect points in our marked set. Right. So, for example, between these 2 points, I've marked this arc A, and I've marked the corresponding arc in the domain surface. And then what we do is we calculate the intersection number of my Jordan curve with this arc. And in this case, on the image pillow, I see that I intersect 1, 2, 3, 4, 5 times. And the intersection with this particular arc is what's telling me my numerator. And then there are several components of the preimage on this side. So we can just pick one. Let's say we look at the red pullback. that's going to have exactly one intersection with my blue arc A. Okay. So since I have exactly one intersection, then that's also necessarily going to be a minimal position. But the story is a little different when I look at these side arcs. On the image side, I'm still fine, right? Everything is in minimal position. I have 2 points of intersection with this green arc B. But for the domain side, even though you can see 2 intersections here and here, that doesn't necessarily mean that the denominator of the corresponding slope is going to be 2. All right, because the intersection number is possibly different from the number of points that we intersect this arc. So I need to ensure, I guess, that this red curve is going to be in minimal position relative to my green curve, up to isotopy. And in fact, I see that. Let me draw a picture. If you follow the trace of this red pullback, then you end up with a bygone on this side. Okay, so relative to my postcritical points, I can actually homotope that bygone to the other side of my green curve. Right, and since it's possible to do this homotopy relative to my postcritical set, the actual intersection number with my green arc B here is going to be 0. Okay, so my R over S on this side is 5/2, but my mu f, my slope pullback function evaluated on that 5/2 will actually be 1/0, or in our notation infinity. Okay, are there any questions about this? All right. So with this example here, it's pretty easy to see what happens when I look at pullbacks of a couple of special curves. All right, so for example, if I look at this horizontal curve that corresponds to R over S being equal to 0/1, then this will actually have these 2 curves in its preimage. And this will have the same slope class as before. Okay, so 0/1 will very clearly be sent to 0/1 under the action of this mu f map. And the same story is going to hold true for the vertical curve 1/0. Right, that's also going to be sent to vertical things. And it's a little bit more difficult to see, but 1/1 will also be sent to 1/1. Now, for more complicated examples, these pictures are a little difficult to produce by hand. So, there are many different ways that you can program mu f to have a computer do this for you automatically. So one way is to do something like we see in this picture is you can imagine, I guess, like a photon bouncing around the boundary of these edges here. All right, and eventually that will close up, and then you can do that on this other side as well. And this is a way, I guess, of evaluating mu f in general, though it's a little inefficient. There are other ways too, but yeah. So here, I guess, is a couple of I guess iterates of different input values from UF. So we see, for example, that 5/21, which would have been quite hard to draw, will actually get sent to 1/3, and then it gets caught in a 1/1 loop. right? And similarly, 17 over 4 will get sent to 5 over 2, but then it gets caught into another invariant loop. And of course, we can have rational numbers that under mu-f eventually end up in this peripheral set. Okay. And, you know, I haven't put down too many examples here, but I hope it's somewhat reasonable to expect that regardless of, you know, where we start R over S, if we iterate enough times, we'll end up in, you know, the same finite set of slope values. This is a pretty famous conjecture called the curve attractor problem. So the conjecture is this. So let's say, you know, we're in our particular setup. There's to map the hyperbolic orbifold. It's realized by rational map. Then we expect there to be some finite set of Jordan curves such that, you know, so long as we're iterating f enough, our pullbacks will eventually end up in this set of Jordan curves. All right, so in our postcritical set being 4 points case, this is equivalent to just saying there's going to be a finite list of rational numbers, so that eventually, you know, mu-f, after we iterate enough times, will always end up in this finite set of rational numbers. So here are a couple of, I guess, special cases where the result is known. I'm not going to go into the details here. This is a bit of an aside. But you know, this is an interesting problem, and a lot of people have been working on it for a while at this point. And it is known that this particular example here satisfies the curve attractor problem. And we'll actually hopefully see a proof of this more or less later on. Okay, so that was our discussion, I guess, of the slope pullback map. But, you know, I mentioned this earlier, there's also a different type of pullback map that we can associate to these Thurston maps, and that's going to be the map on Teichmüller space.
Yeah, sorry, Zach, for the interruption. I think probably we should mention that there is another important class of maps for which the global curve attractor problem is known. It's the polynomial case. Yes.
Yes. Yeah. All right. Thank you, Misha. Okay. So, yeah, in general, it's not known, but a few special cases, I guess, including polynomials, it is known. Okay. So let's, you know, briefly, I guess, recall the definition of Teichmüller space for a sphere. So the Teichmüller space that we associate to a Thurston map is going to be the space of all homeomorphisms phi, orientation preserving, that send our marked sphere to, you know, some standard identification of the Riemann sphere. And it's going to be quotiented by Mobius transformations. Okay, so we'll say that phi1 and phi2 belong to the same equivalence class if there's some Mobius transformation such that phi1 is isotopic to phi2 relative to our postcritical set. Okay. So that was Teichmüller space, but how do you actually get, I guess, a map on Teichmüller space given a Thurston map? Well, here's the process that you follow. So we start off with an element of Teichmüller space tau, and you know, we can suppose that's going to be represented by some map phi here. Again, sending our marked sphere to you know, some standard identification of the Riemann sphere. And then now the composition F composed with phi is also going to be a Thurston map. So we can pull back the complex structure on this set all the way to the sphere over here. And then uniformization says that the sphere equipped with that complex structure is going to be isomorphic to, again, the Riemann sphere with isomorphism phi prime. Okay, so we obtain this commutative diagram where this f tau is, defined to be, I guess, phi prime inverse f phi. And then the point in Teichmüller space that's going to correspond to this phi prime is exactly what we say the, sorry, let me add a subscript here. Well, the image value of the pullback map on Teichmüller space is going to be. So we get some sigma f from Teichmüller space to Teichmüller space, and it maps tau to the tau prime according to this recipe here. Okay, and this map f tau is going to be a rational map. It's going to have the same degree as our Thurston map f, and also, I'm not going to explain the details to this, but this map on Teichmüller space ends up being analytic. Okay, so somehow, like every step in this construction up above is, going to be like an analytic process. So we end up with an analytic map at the end. Okay, but as I said before, we're only interested in 4 postcritical points today. And if you looked at a sphere with 4 marked points, the Teichmüller space for this is very well known, and it's thankfully quite simple. It's just going to be the upper half plane. So our pullback map on Teichmüller space is actually just going to be some analytic map from the upper half plane to the upper half plane. Okay. And there's actually going to be a relationship between this pullback map on Teichmüller space and the slope pullback map that I introduced earlier in the talk. And this was made precise by Nikita Salinger. So it ends up being true that the Weil-Petersen boundary of Teichmüller space is the extended rational numbers, and moreover, our map on Teichmüller space, our sigma f, will actually extend continuously to this Weil-Petersen boundary. Okay, so we're mostly going to actually be interested in, I guess, this this extended map from h bar to h bar. This h bar here is going to be the augmented Teichmüller space. Okay, and then how does this correspondence with my slope map work? Well, it turns out that if you look at sigma f of some rational minus s over r, then this is going to be equal to -1 over mu f of r over s. Okay, so it's going to be conjugate via the map -1 over z, I suppose. Okay, and here's the general theorem that Salinger proved. So we have a continuous extension of the Weil-Petersen boundary, and it's going to map, I guess this is the strata of the curve into the strata of the curve pullback. Okay. So we're going to study, I guess, this map on Teichmüller space a little bit. But before we do that, I need to, introduce an auxiliary space here that will be useful for our calculations, which is the moduli space. So the moduli space is just going to be the set of injections from our postcritical set, our 4 marked points into the Riemann sphere. All right, and as usual, this is going to be quotiented out by things isotopic relative to the postcritical set up to post-composition with Mobius transformation. Okay. And if you examine this definition closely, you'll see that really what this space boils down to is, restriction of one of these maps to PF. So with that in hand, you can actually observe that Teichmüller space is going to be the universal cover of the moduli space. And the corresponding covering map is just going to send, our phi, our representative, to the restriction of phi to just our postcritical set. Okay, so that's moduli space. And if in one of our spheres here, with 4 marked points, I declare that 3 of those marked points are going to be 0, 1, and infinity, then this is actually going to define an isomorphism from moduli space to the Riemann sphere minus those 3 points. The reason being that, if I declare that A, B, C get mapped to specifically 0, 1, infinity, well, that uniquely determines a Mobius transformation. Okay, so the way this isomorphism works is it's going to send, I guess, this 4th postcritical point to whatever the image under that Mobius transformation is, and that's going to be a point in this set here. Okay. So with that in hand, let's return to our example before, this T-shaped map. And let's go ahead and, normalize the positions of our postcritical points, right? So we're going to have 0, 1, infinity is 3 of them. And let's try and find a rational map that models the behavior of the map as I've written it down. Okay, so we're imagining we have separate points Z0 and W0 here. So what are things that we know about this map? Capital F. So the degree of it is going to be 4, right? Just by looking at the number of tiles on this side. And we can also write down the critical portrait. So 0 we see gets mapped to 0 with degree 3. 1 gets mapped to 1 with, again, degree 3. Infinity gets mapped to infinity, degree 2. In my labeling, at least, Z0 will get mapped to W0 with degree 2. All right. So this actually restricts what the form of the map should be by quite a bit. So again, we're looking for a rational map F that satisfies these properties. Let me move this out. So for example, the fact that infinity gets mapped to infinity with degree 2 tells me that the degree of my numerator must exceed the degree of my denominator. I mean, it must exceed the degree by exactly 2. So we'll have some quotient here of 2 polynomials. I want a degree 4 polynomial on the top and a degree 2 polynomial on the bottom. And I can also, very easily use this information about the location of, or sorry, I guess the degree of, 0 as my critical point. So since 0 is a critical point of degree 3, then I actually get a z cubed upstairs. All right, and since I know that the numerator is supposed to be in total degree 4, then that means I only have a linear term left over here. Right, and then I guess we can assume that we have some arbitrary quadratic downstairs. All right, and A, B, C, D are, complex numbers. So that's our current candidate. But, we have more information we can use, right? So I haven't used yet, for example, that 1 gets mapped to 1, and that it's also going to be a critical point of degree 3. So we can write those down, and I'm not going to because it gets rather tedious. But we have 4 unknowns here, and this corresponds to 3 equations involving A, B, C, D. So in principle, it should be possible to solve for 3 of these parameters in terms of the remaining one. And if you sit down and you bash through the algebra, this does end up being the case. So B can be chosen to be minus 2a plus 1/3. C can be minus 2a minus 1, and D can be a plus 1/3. All right, and I need to exclude a from being 1/3. If a were 1/3, then some sort of degeneracy happens. So I toss that out. Okay, so the I guess current guess for the rational map that models this map here is this thing. And now that I've written all that down, I can determine a relationship between this parameter A and our remaining critical point Z0 by using this f prime Z0 is equal to 0 equation. So again, I'm not going to write down the algebra for it because taking the derivative of this thing is a bit of a pain. But if you write down the equation and you solve for Z0 in terms of A, you'll obtain something like this. Right, and then once you have that Z0 in hand, then you can actually say what W0 ought to be as well, just by taking the image of that point. Okay, so this is what Z0 and W0 are in terms of our remaining parameter A. Okay, so now unfortunately I have to go on a bit of an aside. So I'm going to skip over a lot of details here, and I apologize for being vague, but there's a good chunk to get through still. But there's going to be an intermediate complex manifold called the Hurwitz space that I can place here in the middle of this diagram. And it ends up being the case that this Hurwitz space is going to be naturally isomorphic to the upper half plane modulo this group gamma. And this group gamma is going to correspond, I guess, to a group action on the upper half plane. So it's going to be a subgroup of SL2Z. And it's going to have the property, I guess, that there's going to be a pseudo equivariance relation for our map sigma f relative to this group. So I'm just going to write this in because I ran out of room for it on the slide. But let's say I have a point Teichmüller space tau, and then I'm acting on it by some element of this group gamma, which again you can think of as I guess an element of SL2Z up in the upper half plane. Then there's some map called the virtual endomorphism, phi f, for which we get this functional equation, basically. Okay. And this virtual endomorphism, unfortunately, is not going to be defined on the entirety of SL2Z. It's only going to be defined on a special subgroup, which is going to be the group of liftables. But I'm going to be vague here, and I apologize. None of this is very formal or rigorous or detailed, but we're going to move on nonetheless. Okay. So if you look at these maps for Z naught and W naught that we computed in terms of our parameter array, we can, I guess, look at what happens when I take the upper half plane and I pull it back through these maps into this this WF Hurwitz space. So I've plotted these here, and we get some kind of, I guess, triangulation in this Hurwitz space. So yeah, we'll use this in a second. Okay. So as I pointed out at the beginning, when we look at this map in Teichmüller space, there's going to be a fixed point exactly when our Thurston map is realized by rational map. And we are in this situation. So there's going to be a fixed map in Teichmüller space, and it just so happens that by reasons I won't get into, we can say exactly where this fixed point for the sigma F map is. It's going to be somewhere on the imaginary axis. Okay. But if I look at, I guess, this tiling I get in my Hurwitz space, then it's possible to, I guess, lift this tiling to some collection of triangles in Teichmüller space. So it's possible to calculate the location of our critical point in Teichmüller space. It's going to be somewhere here along the negative axis. And since I know, that this thing and also this 0, 1 infinity triangle both need to map to the upper half plane in my commutative diagram, I can identify this edge here with this edge here. And it turns out if you identify, I guess, certain pairs of edges in this fairy triangulation, we can draw a curve in this parameter space. And then each segment of this curve is going to correspond, I guess, to some element in the triangulation, some boundary edge in this triangulation in this upper half plane model I have here. So for example, on this blue arc, I will have something like this. And then I have the green. I only go halfway there. And then there's a purple line here. And this actually ends up just going straight up like this. Okay. Yeah, if you identify the I guess edges in this Fourier triangulation appropriately, you'll get a picture that looks exactly like this. Okay. So this turns out to correspond to a fundamental domain for our sigma F map relative to the action by this virtual endomorphism domain. So let me write it down again. Okay, so yeah, we're acting by a group gamma. It's a subgroup of SL2Z. It's going to be a finite index subgroup, which means it's going to be a Fuchsian group, if you're familiar with the theory of Fuchsian groups. So it's possible to draw a fundamental domain in the upper half plane. So, in principle, if I understand where my sigma F maps just this stuff here, right, between all of my colored edges, then I can use this pseudo equivariance property to figure out where sigma F sends everything else as well. Okay. But in my correspondence, my lines here are actually, sharing a common space with my tiling relative to Z naught inverse of H. All right, so they're both living in Hurwitz space. Okay, so we see here that based off of the properties of this map, we can make a prediction, I guess, of what the boundary of the image for this fundamental domain I've drawn will be. So yeah, let me copy this again. There we go. Okay. So it ends up being the case that we're just going to stay on and inside the boundary of our 0, 1, infinity triangle according to this picture here. So we end up doing something like this. And unfortunately, I'm not going to color code the sides for you. But, for example, well, maybe I'll do at least one. So this red edge here gets sent to this red edge here. To allow me to change the color of this. Maybe not. And then the blue here gets sent to up here, basically. The green will go from this peripheral element down to here, and then it goes up. And then for the pink, we go down from infinity to some critical point, then we go back up. Okay, so the image, I guess, of this fundamental domain is going to lie entirely within this slit modular triangle here. And I want to talk more about this, but unfortunately, I think I'm nearly out of time. The one thing I'll mention here, I guess, is, since, the action, I guess, on this fundamental domain determines my pullback map on Teichmüller space, we can imagine, I guess, any other cusp here as, a cusp on the corner of some translate of this fundamental domain, essentially, with respect to the group of liftables. Okay, so in principle, for a point, let's say over here, it'll be possible to write this as g dot tau of some cusp that lies properly inside or on the edge rather of this fundamental domain here. So I could have T naught here. Okay. And we know, I guess, that this target is living strictly inside this fundamental domain that I've drawn. So if you work through the details, it turns out that because the image of my fundamental domain lies in the fundamental domain itself, this will imply that the curve attractor conjecture is true. All right, so if I take a cusp and I iterate it often enough, I'll eventually end up as one of the cusps on my fundamental domain. And the reason why we end up in specifically these triangles when I iterate is because these triangles have a fixed point that happens to be attracting. Yeah, so that's it for now.